So where we were last time is I showed you an idea where you can represent almost any function with an arbitrarily high degree polynomial. So here I'm making a 4th degree polynomial representation for e to the 2x. And the idea of the process is you're going to set all of the derivatives of your function and the representation function. You're going to set all the derivatives at x equals 0 to be the same, because we want our representation to have the same y value as the original function. We want the slope to be the same. We want the slope's rate of change to be the same. We want the rate of change of the slope's rate of change to be the same. And in general, each of the derivatives is saying what's the rate of change of the prior thing. So by setting more and more of these derivatives to be the same, we're just trying to tell our polynomial that it needs to match how this function is changing as close as possible. All of these rates of change and rates of change need to match each other. So starting from this starting point, all of this work here was just working out these equations. I was finding all the derivatives for f and setting them all equal to 0 here. I was finding all the derivatives of p and setting them all equal to 0. And that lets me solve for all of these coefficients, which are the numbers that eventually construct my polynomial. And we ended by observing that there's a pattern in both sides here, and you can use that pattern to write a general formula for what will the nth coefficient look like. And our nth coefficient for e to the 2x was 2 to the n divided by n factorial. So if you want to, you can actually graph these in Desmos very easily. Here I'm using the sigma summation notation, and I have, you'll notice this is my general equation for the nth coefficient, and then x to the n. So here, when n goes from 0 to d, I can drag d to a 1st degree representation, 2nd, 3rd, 4th, 5th, 6th. So it's graphing exactly the coefficients that I solved for in the last screen. And you can see that as my degree gets higher, I got a parabola, a cubic, a 4th degree, and you see that my representation is getting closer and closer. And if I wanted to, there's no reason to stop at 6. The only thing that's limiting us is the computational speed of the computer. But so if I were going to do a 42nd degree polynomial, you see that that's accurate all the way down to there. And as I keep adding terms, we eventually reach close to the limit of this machine's capability, but it looks like my polynomial matches the original function quite a way out. But the whole process started by building a representation at x equals 0. And we realized that that's going to be a problem if I want to build a series representation for something that is undefined at x equals 0, or for something where it's got a vertical tangent line, like this one at x equals 0, because then the first derivative won't exist. So it would be very convenient if we were able to build our representation starting not at x equals 0, but starting somewhere else. So let's look and see why was 0 so special. Why did we use 0? Imagine we were going to do this same process, but instead of setting y values equal and first derivatives equal and so on at 0, imagine we were going to try and do it all at 1. So we were going to try and build a representation at 1. Well, what would happen? On this side, it doesn't seem like there's going to be any problem. I'll plug in 1, and then here instead of, so I'll get e to the 2 times 1. So instead of 1, on this side, I'd just have e squared. And on this side, I'd have 2 times e squared. And on this side, I'd have 4 times e squared. So far, no problem. Okay, what about this side? Well, when I plug in 1 for x on this side, what was nice about 0 is 0 made all of these terms drop out so that I just had my first coefficient here. If I plug in 1, I don't have such a nice equation anymore. Now I've got a0 plus, let's see, a1 times 1 plus a2 times 1 plus a3 times 1, and so on. So I would have this equation, with all of my coefficients in it. And then same thing, for the next one I would plug it in and I would have all 1s. As long as we're only doing a small number of terms, you might imagine going all the way to the end there and think, well, hold on, this is still going to work out. Because in the last derivative, we only have one term, so that would let us solve for a sub 4, and then you could plug that back in the previous equation. So maybe you could work your way backwards and plug in the ones you've solved for, and eventually work your way back to the first one, and you would know all of the coefficients. And that would work. But really what you're talking about doing is, you're talking about solving 5 equations with 5 unknown variables. Or if you were going to find a higher degree polynomial, you would be solving for 10 equations with 10 unknown variables. So you'd be solving huge systems. So it's possible, but it seems like maybe there might be an easier way. So the heart of the easier way is, what if we were going to rewrite the original polynomial so that when we plug in 1, the original trick with 0 still works? The original trick with 0 was when you plugged in 0, most of the terms disappear because their values end up being 0. Well, what if I could rewrite this so that when I plug in 1, most of my terms disappear? So let's do the same process. Only this time, my polynomial, instead of looking like using a polynomial where all the coefficients are coefficients on x and x squared and x cubed, we'll use a polynomial that looks like this, where all of the coefficients we're solving for are coefficients on different powers of x minus 1. So in the original polynomial, when I plug in 0, all the terms with x disappear. Here, if I plug in x equals 1, then any term with an x minus 1 will evaluate to 0, and all of those terms will disappear. So you see, it's going to let us do the exact same trick that worked before, only now we can use a value of x that's different from 0. So let's work through the same process. All these derivatives are going to be the same as last time. So if f was e to the 2x, f prime is 2e to the 2x, 4e to the 2x, 8e to the 2x, 16e to the 2x. And if I evaluate each of those at x equals 1, that gives me e squared, 2e squared, 4e squared, 8e squared, and 16e squared. Okay, now let's look at the right-hand side. So if I evaluate this polynomial at x equals 1, all of these terms with x minus 1s evaluate to 0, so I'm left over with just a sub 0, the same way that we had last time. Alright, let's take the derivative of this and just make sure that the same thing is going to happen. So p prime, let's see, if you imagine taking the derivative of this, you could imagine distributing, and then you'd have a1x, and the derivative of that is just a sub 1. If I'm going to take the derivative of this term, I'm going to need to use the chain rule. So first it's power rule, so 2 will come down, and I'll have 2a sub 2 times x minus 1. But then I need to multiply by the derivative of the inside. But as you can see, the derivative of the inside is just 1, because the derivative of x minus 1 is 1. So then here the 3 comes down, so 3a sub 3, x minus 1 squared, and so on. So if I plug in x equals 1 here, exact same thing as last time. All the terms with x minus 1 evaluate to 0, and I'm left over with a sub 1 here. Let's do one more, and then you'll see the general pattern. So I'll take the derivative again. Here I've got 2a sub 2. Here for this term, the 2 comes down, so I've got 3 times 2, x minus 1 to the first power. I got to use the chain rule by multiplying by the inside function, the derivative of the inside function, but the derivative of the inside function is still just 1. And so then when I evaluate p double prime at x equals 1, This term drops out, all the rest of them drop out, and I've got 2a sub 2. So you'll notice that this is coming out to be exactly the same as last time when we were evaluating at x equals 0. I've got a0, a1, 2a sub 2, and hopefully you'll see that what's producing these coefficients is exactly the same. So here I should expect to get 3 factorial a sub 3, 4 factorial a sub 4. So if I was going to write the nth term, on this side, it looks like I've got 2 to the n e squared coming from there. And on this side, I've got n factorial a sub n. So if I wanted to write my new series, it looks like it's going to be e squared plus 2e squared x minus 1 plus 4e squared over 2 x minus 1 squared plus 8e squared over 3 factorial x minus 1 cubed, and so on. And the nth term is, where did I do it? Okay. So I'm solving for this equation. I'm solving this equation here for a sub n. So I'm going to divide both sides by n factorial. And I'll get the nth coefficient is 2 to the n e squared over n factorial. So if that's the nth coefficient, 2 to the n e squared over n factorial, the nth term is that coefficient times x minus 1 to the nth power. So now this is a complete series, only now we haven't centered our representation at x equals 0, we've centered our representation at x equals 1. Let's just take a quick look at what that looks like in Desmos. Here's our function, e to the 2x, and I'm going to start typing in each term of the polynomial that we solved for. So we've got e squared, and as you can see, the y values are the same at x equals 1. Now let's add another term, 2e squared times x minus 1. And this looks like it's a tangent line constructed exactly at x equals 1. Let's add another term, 4e squared divided by 2, x minus 1 squared. So now I've got a quadratic representation. Instead of typing each term in by hand, let's use the summation because that's a little bit faster. So my n values are going to go from 0 to, let's say, 5. And the general term for my coefficient was 2 to the n times e squared divided by n factorial. And then each term was an x minus 1 to the nth power. So here I've just rescaled my axes so that it's a little bit easier to see. Instead of doing a 5th degree, let's do a degree d, and then I'll have a slider for d, which will go from degree 0 up to degree 10. So there my first degree is a tangent line, quadratic, cubic, 4th degree, 5th degree. And so this looks just like it did before, only now it's all centered around x equals 1 instead of x equals 0.